this easier UVM sequences as the SystemVerilog UVM sequence and task equivalence. The easier abstract SystemVerilog UVM sequence are a powerful way to model stimulus and response for functional verification. Unfortunately, using SystemVerilog UVM sequences can require extensive background in SystemVerilog, the UVM, and object-oriented programming. This paper explains a collection of techniques to allow the power of sequences and with the familiarity and simplicity of calling tasks. Familiarity. Background. Using SystemVerilog UVM, sequences can be built to provide stimulus and checking capabilities for test and verification IP. These sequences allow for powerful control over randomization and generation of scenarios for test stimulus. The verification IP is used to simplify the verification task. Furthermore, an AMBA AXI verification IP can be used to generate AXI traffic, or send simple burst commands, or even just one transfer a single channel. Today's verification IP is being packaged with the UVM sequences as a way to control the IP. Providing sequences as a way to control the verification IP allows full flexibility for powerful stimulus generation. Unfortunately, using a sequence interface for verification IP may require knowledge about SystemVerilog, randomization, constraint, object-oriented programming, and detailed UVM. Many verification teams lack this knowledge. This knowledge gap can be filled with a simple task-based interface around the UVM sequence-based verification IP. The remainder of this paper will describe such as an interface and provide examples using it. These techniques can be adopted for any SystemVerilog UVM sequence interface. The Verilog tasks. The Verilog language has contained tasks since its beginning. A task is a collection of statements that perform some common function. Furthermore, a task is different than a Verilog function in that it can consume time. The task above is named read, and takes two arguments. The first argument, ADDR, is an input to a task. The second argument, data, is an output from the task. The task body performed the desired functionality. In this case, performing a read on a bus by replacing the address on the bus and setting the bus RW signal, then waiting for 2 clocks. After the second clock, the data is retrieved from the bus and assigned to the data return argument. Then the task returns. Sequences. A sequence is really just a fancy name for a function or a task call. It's called a sequence because its main use is to generate a sequence of transactions. The sequence could be from 1 to n transactions or could be no transactions. A transaction is just an abstraction of some communication. For example, write 3420 is a transaction that tells a component to write address 34 with a value 20. A simple sequence might iterate through an address range, first writing, then reading and checking the value read against the value written. Such a sequence is listed below as RW sequence. And The sequence above is a class definition named RW sequence, which contains three member variables: low address, high address, and data. They are each random variable and may have constraints such as the var constraint, which controls the values of low address and high address. The low address must be 0 or greater. A high address must be greater than low address and must be less than the 256. The body task is simple. It goes through each address between low address and high address, issuing a write, then a read, follow a check. Next is sequence and task equivalence. Given the sequence above, you could imagine a task named RW implemented as: this task first constructs a new sequence, and then the field in the sequence member variables with values from the task argument. Then the task calls a start sequence. Calling a start means the sequence will execute. The body task of the sequence will be called. This task is a simple gasket used to fill the gap between the task-based word and the sequence-based word. Not every verification engineer will need to write a task like this. A verification IP developer may include this layer with the UVM sequences for ease of use, or a test bench architect may create this layer for internal use of the verification team. The simple tasks with arguments. A simple task with argument was demonstrated above in read task and RW task. Decide the input argument and the output argument. A task can also have a REF argument. Input arguments are passed copied into the task. Output arguments are passed out, copied out of the task. These arguments are passed by value, and the task gets a copy of the input values and return a copy of the output. The potential exists for a lot of copies data. SystemVerilog also allows the task's argument to be references, REF arguments. No copy is made, and a value can be passed in, and a changed value can be returned. REF arguments are passed by reference. REF arguments are convenient for arguments that have an input value which will be modified, or an argument that are large. Once the task arguments have their types and the input-output REF decided, that it is a simple matter of transferring the data from the task argument to class member variables. The task input argument should be copied to the sequence rand variables. After the sequence has been run, after the sequence start or returns, the output class member variables are assigned to the task output variables. See the read task below for an input variable. A simple read task and write task invoking the read sequence and the write sequence respectively. In the code block below, the task RW is encoded with the 4 argument. The RW task has been changed to have an argument and named CRC. The CRC is returned, and the sum is created as loop progresses. The sequence member variables. In a sequence, member variables are the input and output. A variable marked rand is thought of an input variable. It is a variable that can be randomized and take different values. A variable is not marked rand is thought as an output variable. It is the result of value of the operation. When the number of the argument gets large, or the data type of the argument gets large, such as a large array of data, it can be useful to use the sequence directory and not even having the task. The sequence handler can be constructed, randomized, and started by the inline test code. Using a sequence handler directly. A task call is a convenient way to hide the complexity of the sequence, but in addition to simplifying, It has also removed much of the power of the sequences. A sequence handler can be used directly, accessing the field of the sequence as when needed. Declare the sequence S, construct the sequences S. Assign the class member variables in S, row address and a high address. Start a sequence of the proper sequencer. Retrieve the many calculated or the or value, CRC in this case. Randomize a sequence handle. A task with the argument provides a way to interface to a sequence with the member variables, but misses out one of the most powerful parts of sequences, randomization of member variables. In the code below, the sequences is declared, and the sequence S, sorry, not sequences, sequence S is constructed and then randomized each time through the for loop. After randomized, the sequence is started on the proper sequencer. The container module. Tasks provide a familiar way to interact with the UVM sequences. There are some minor details must be managed. The sequence runs on a sequencer. A sequencer is a part of the design of the UVM agent-based verification IP. Task, UVM agent, sequence. Figure 1 is task interacting with the VIP agent. When we said a sequence runs on a sequencer, we mean the under normal circumstances, the sequence requests access to a driver while allowing the sequencer to arbitrate request for the task to send request and get responses from the driver, and it also needs to have a sequencer. The task-based simplification needs to have a sequencer handle variables. This is most easy to by using a container like a module. The module M below is such a module. Module M contains a sequencer name and the sequencer handle. The seq handle will be filled in based on the call. The UVM find command, and before the find command or any part of the UVM can be used, we must be sure and what state it is in. We synchronize with the UVM using the wait for state call to the wait until the UVM phase in the engine until the run phase started state. Once it has entered the state, we are guaranteed that the components are built and ready to use. So we instantiated this module like other Verilog module, and we use the UVM find command to find the proper sequencer and save a handle to it. Now we can say this is a module instance is connected to or can make a request of a sequencer, and it can send a transaction to the driver. So now the module M contains tasks which act as a gasket to the sequences. The task read and write below build a sequence of the appropriate type, read a sequence or write a sequence by calling new. Before we use start to call to the long sequences, and we synchronize with the UVM to make sure we are in a known state. Run phase, UVM phase started. After the sequence is constructed, we copy the task argument into a sequence and class member variables. Then we call a s-starts SQR, which causes the sequence names S to be run on the sequence SQR. Internal UVM plumbing will cause the sequence body routine to be called, and the body task is the definition of this sequence. The body task is the below. The body task is the behavior. After start returns, the sequence has completed execution. At the time, we can copy the data value from the sequence class member variable into output argument data. The container module could be a SystemVerilog interface or a class, It doesn't matter as long as a container is used to help manage things like the sequencer name and handle, and is used to contain the tasks that are valid with this particular interface and the collection of sequences. Using the container module. The container module is instantiated just like any Verilog module. In the code below, we have two instances of module M underscore A and M underscore B. The initial block begins by setting the sequencer name and that each module instances should be connected to. One module connected to one interface. The synchronization with the UVM phase. Using wait for state, the code synchronized with the UVM learn phase. Once synchronized, the first thing that happens in the test bench is that an objection is raised. This is a UVM mechanism to end simulation. Simulation will end when no objections are raised. So the method is raised the objection and do the test. Load the objection, wait for an objection to end exit simulation. And figure 2, VIP agent-based test. The sequencer is just an arbiter which arbitrates multiple sequences with agile access to the driver. The sequencer can be retrieved in many ways. The example below uses find. Summary. The SystemVerilog UVM sequences are very powerful, but are sometimes more complex than the users are comfortable with. Using a task-based interface can fill the complexity gap by providing a more familiar use of, while at the same time preserving the power of sequences. Both task-based interface and the sequences can be used alongside each other. Okay, thank you.